graphs like matchings, connectedness, and so on. So you're going to get back to connectivity in graphs. So we all recall, right, what a connected graph is? Do any of you recall? So when do you say an undirected graph G is connected?
Between any two vertices, there is a path.
So you say a graph is connected if there exists a path between any pair of distinct vertices. That's what we saw. We saw some examples of connected graphs and connected components of the graphs. So now today we are going to try and answer this simple question that how connected is a given graph? Right? How much connected is a given graph? That's the right way to. So what do we mean by how much connected? Right? So you can either say a graph is connected or you would say that the graph is disconnected. For example, this graph. Let's just this one is connected. Whereas if you look at this graph, this one. This one contains two connected components. This is component C1, this is component C2. So this graph you can say is disconnected because from this vertex to this vertex, there is no path. This graph is connected. But let's say you're given a connected graph itself. For example, let's call this G1, let's call this G2. I'm going to draw another graph, say G3. So make this complete. Just for. So this is K5. Right? If you recall, this is the complete graph on 5 vertices. So now amongst these two graphs, somebody asked you which graph is more connected, right? What would be your answer? Is it G1 or G3? At least intuitively, maybe even if you don't know the definition. This looks like a dense graph, right? There are so many edges, whereas here there are far few edges than the complete graph on 5 vertices. In fact, we can also consider just these 5 vertices and maybe this edge, the edges in red. That also as an example. So which is more connected? Is it K5 or the graph on 5 vertices that I just drew? So one way to think about it is there are these nice vertices here, right? So let's think of this as a computer network, right? You have computers at each of these places. And let's say you have fiber optic cables running between them or some sort of a connection between them. Packets are sent from this client to this client to this client and so on. Right? Now suppose, let's just name them A, B, C, D. These are the 5 computers. And one of them failed. Let's say C fails for now. So this is down right now. The server is down. So is there still a path between the other vertices? This guy we've already lost him, so it's okay. But amongst the other vertices, can packets still be transmitted?
Yes.
Whereas in this graph, let's say this node, right? This person is some critical person and he just failed. So now we can no longer transmit packets, right? So in the sense that he was so critical, this vertex was quite important. In the sense that if you remove this vertex, then the graph gets disconnected. Whereas in this graph, no matter which vertex you remove, the graph will still remain connected. That is what we mean by how much connected is a graph. So now this set of vertices, right, this vertex has a special significance to the graph G3. So what is that? That is what we want to try and formalize. So you say a set of vertices S, this is a subset of B. So throughout we will go back to this notation that G is the set of vertices and a set of edges. For today's lecture we will only talk about undirected graphs, but whatever I say about undirected graphs will also hold for directed graphs. So you say a set of vertices is a cut set. If you look at the graph G minus the set S, this graph is disconnected. Then you call those set of vertices a cut set. So when I say G minus S, what do I mean by that? You remove the vertices in S and all incident edges. No dangling edges. All edges incident on vertices in S. If you remove them, the graph will become disconnected. So such a set is called a cut set. So now can someone say what is one cut set in G3? Let me just call this. In G3, what's a cut set?
Set C.
Just the vertex C, right? So if I remove C and all these four edges, then the graph will become disconnected. Whereas if I remove E or I, there will be no issue. So about K5, the complete graph, right? G1, can someone say what is this?
The whole graph.
Right. So you have to remove all the vertices, right? Or in some sense, you have to, as long as only one vertex remains, everything is going to remain connected even if you remove. Right? So it's only like A, B, C, D. So you have to make the graph empty or the null graph. Only then the graph can be disconnected. But this is sort of costly in the sense that you have to induce edges between all pairs of vertices in order to ensure that there is a lot of connectivity. So these things have real applications. Like for example, if you want to design, let's say, a computer network, right? You should ensure that the size of the cut set is reasonably large. Otherwise, even if one computer just goes down, then you will lose all links. Right? Similarly, in a road network, but there might still be these crucial things, right? Crucial junctions. One of the roads fail, then you cannot reach the other part. So these have some real-time applications. We want to understand, given a graph, what is the cut set, or how do you, what are some properties of the cut set? And sometimes the set S of vertices is also called cut vertices instead of cut set, or articulation points. These are like additional terminology. So some books might use these interchangeably. Some books might call it cut vertices. Some of them might call it articulation points. So now, what's the sanctity of vertices here? You can try to define the same thing for edges also, right? For example, let's say I lose this edge, right? This link fails, sort of. That's also possible. Like some road just caved in, or some computer link just failed. Right? So then is the graph disconnected?
No.
Whereas if this link fails, right, there is no path from A to D. So the graph becomes disconnected. Right? So for edges also, you can define a similar notion. Let's do that. So you say a set of edges can also be removed from the graph, and such. So let's see, set of edges. Let me just call it E prime. H cut. If G minus E. So what I mean by G minus E is actually E minus E prime. So you look at the same graph. The vertices are the same, but now you look at E minus E prime. This graph, let's call this E prime, is disconnected. So you remove a set of edges that leaves the remaining graph disconnected. Right? It's called an edge cut. Some books called it the bridge set. So this terminology basically came from this sort of a graph. Right? For example, if you have, was there a question? Okay, yeah. So this one, right? So this edge is called a bridge, some sort of an essential connection, right, between these two things. It just looks like a real-time bridge. This set is also called a bridge set. So is the definition clear? What is a cut set and what is a edge cut or a bridge set?
Yes, ma'am.
Okay. Okay, good. So now we want to understand, what do we mean by how much connected the graph is? So intuitively, what does it mean? If the size, so for now, let us focus on cut set of vertices. For now, this for next like some 15-20 minutes, we are only going to talk about cut set of vertices. Right? So that is what given a graph, what set of vertices should you remove from the graph in order to disconnect the graph. So you must remember that when you remove a vertex, you're going to remove all the incident edges. That's what we mean by removing a vertex. Right? So I will try to give you some graphs and you have to figure out what is a cut set and what are its properties. So for example, for the complete graph, right, you have to the complete graph has no cut vertices. Right? You have to remove all the vertices in the graph. So this way, you can measure how connected a graph is, right, based on the size of the cut set. Also, so you can think about it this way. So there can be graphs, for example, even this, right? Let's look at, maybe let me try to draw. Let's see. So is there one vertex that you can remove? Right? I think I should edit it. Let's see. Trying to draw an example. I hope it works. So is there one vertex that you can remove that disconnects the graph?
The one with degree.
This one. Right? Okay. So if you remove this, it gets disconnected. Now there can be graphs where removal of no one vertex will disconnect the graph. But if you remove two vertices, you can disconnect the graph. That is reasonable, right? That can happen. For example, let's try to see if I can frame an example. I'm going to try and see an example. Let's see if it works. For example, this one. So here, no one vertex is a cut vertex, right? So if you remove any one vertex, the graph will still remain connected. But if I remove these two vertices, then the graph becomes disconnected. So you can define the size of a cut set. Given a graph, what's the smallest number of vertices you have to remove from the graph in order to disconnect the graph. And that is what is called the connectivity of a graph. So that is how much connected the graph is. If you have to remove all the vertices to disconnect the graph, then the graph is so connected, right? You have to expend a lot, all the computers should come down, all the links should go down, or all the servers should go down in order to disconnect the network. Right? So that is what we mean by connectivity of a graph. So given a graph G, you can define the connectivity of G. This is often denoted by the letter kappa. So kappa of G. So this is the minimum number of vertices to be removed from G in order to disconnect. So you can also think about the size of the smallest cut, vertex cut. Is this definition clear? So for example, what is the connectivity of the complete graph on n vertices? Okay. So we will usually say it is n minus 1 in the sense that one vertex will remain, right? So it's sort of disconnected. So as long as you isolate that vertex, you can say that the graph is disconnected because we are looking at simple undirected graphs and there is no path from that vertex to itself. So but that's only a matter of terminology. It's okay. Right? But for example, let's take bipartite graphs, complete bipartite graphs, KM. You'll have to remove the smaller set, right? At least you have to remove those many vertices in order to disconnect the graph. So this way you can define the connectivity of a graph. So how large can the connectivity be? So generally for any graph G, it has to be at most n minus 1. Right? So either you remove everything and just you are left with just one vertex, or you can do better. It's at least 0. This is an inequality we have about the connectivity. This is probably the first inequality. Right? We will try to refine this. And based on the connectivity, you can say that a graph is this much connected, right? So what you can say is a graph is k connected. Sorry, k connected if you have to remove at least k vertices in order to disconnect the graph. So kappa of g is at least. Right? So sometimes in order to make things clear, we say k vertex connected because we will have a similar definition for edge connected also, which we'll see later. So what does k connected mean? That is, you have to remove at least k vertices in order to disconnect the graph, which means that there is no cut set of size k minus 1. Is this definition clear? Okay. So you can have graphs that are two connected, but not one connected. So you have to like remove at least so many vertices from the graph. So this is kappa of g. So similarly, you can also define the edge connectivity. So let's say graph G. So what is the edge connectivity of G? So this is vertex connectivity of G. So I will write vertex connectivity. We're going to talk about the edge connectivity of G. So what do you think it is? What should it, the definition be? Given that we know what vertex connectivity is. This is the minimum number of vertices you have to remove in order to disconnect the graph. Now what should this definition be? Okay, anybody wants to try the definition? What is edge connectivity? Yeah, if you can't try this, it means this is not clear to you.
The minimum number of edges to be removed.
Right, right. So the minimum number of edges you can remove, right? In order to disconnect the graph. So it's the size of the smallest edge cut. And this is denoted by lambda of g. So now we have a lot of things, right? So we defined what connectivity of a graph is, what is vertex connectivity, what is edge connectivity. So the question is, what is the relationship between kappa of g and lambda of g? Okay. So before this, what did we see? So we saw that kappa of g can be at most n minus 1, right? Or it can be at most n, the way you think about it. Let's say we have a graph. There are some d vertices. D, this vertex b has degree d, and everything else probably has degree less than d. So all of these have vertices that have less than. So now, how large can lambda of g be? So this is the vertex of the maximum degree, and this vertex b has degree d. Every other vertex in the graph has degree less than. Suppose I tell you this, how large can lambda of g?
Less than equal to D.
Less than or equal to d, right? Because it's the smallest number of vertices you have to remove in order to disconnect the graph. If you remove all the edges incident on b, then you will be left with a disconnected graph. So it can be at most d. Of course, you can do better. Maybe there is another nice choice of edges that you can take to disconnect the graph. But definitely this one disconnects the graph, right? If you remove all of them, then B is separate from the rest of the graph. Right? So lambda of G is at most B. Now, can someone do the same argument for kappa of G? How large can it be if the maximum degree is B? How large can it be?
We can remove all the edges incidentally.
Sorry?
We can remove all the edges incident to V.
No, so kappa of G, you are supposed to remove the vertices, right?
Okay, so you can remove all the vertices incident to V.
Correct. So you can remove all the neighbors of B. That's what you're suggesting, right?
Yeah.
Right. Correct. So what can one do? You can just remove all these vertices. There are D of them. And this will disconnect the graph. This will disconnect B from the rest of the graph. So the graph is disconnected. So kappa of G is at most. So n minus 1 is a very loose bound. So what we have is lambda of G is less than or equal to the maximum overall D, maximum overall B in the degree of B. Similarly, kappa of G also is. So agreed, all of you on this? If there are any questions, you can take. So it's actually not. Sorry?
Isn't minimum a better bound? Why are we going with maximum?
Yes, even I thought so.
Sorry. Yeah. It's at most. B degree of. That's right. And kappa of G also, this is true. So now the question is, what is the connection between these two? So this, what is that? What's the direction of the inequality here? Is this clear? Yeah, it should be minimum degree. As in, everything else has degree greater than reversal. This is the one with the smallest degree, so it's enough to actually remove this. Yeah. Okay, so I will try to fill this up. So this is what we want to fill. The answer to this is less than or equal to. Right, so what do we mean by this? That is, if you have an edge set, right, that separates the graph of size, let's say L, then you can also construct a set of vertices of the same of size at most that will whose removal will disconnect the graph. This is actually not very surprising, because if you can remove these bridges, right, intuitively, if these edges are somehow the links that you want to disconnect, then you can look at this road and look at the poles. One of the pole, if you remove also, you will disconnect the graph, because this one was part of an edge cut. Okay, but you will need some more terminology to prove this. Okay, that's what we want. But is the question clear what we are trying to prove? So the thing is, for any graph, see, let's say at least two vertices. Think 2 is fine. Of G is less than or equal to lambda of G. So to show this, what I need to show is, if I have an edge set of size, so given an edge cut, so it's a set of edges that you can remove to disconnect the graph of size L. You want to construct a vertex cut of size at most L. Right, so this is what we want to do. Is the goal clear? Does anybody want to try? What do you think we should do? So we have an edge cut, right? So let's name the edge cut. Let's call it C. So let C be the edge cut. let's call this edge cut. So it's a set of edges that disconnect the graph. Edge cut in G.
Ma'am, this is just a guess. For
Uh-huh.
any two edges part of like that are part of C, um, like there has to be two vertices, one belonging to each that are connected by an edge.
Okay. Right. One belonging to some set, right? That's what.
Yeah.
Right. Okay. So let's try to formally write down what we just said. So C is an edge cut. So what you know is if I remove the edges in C, the graph will become disconnected. So this set C definitely separates a set of vertices S from the remaining set, right? From V minus S. So in other words, you have something like this. Right? So there is this graph and there are some vertices here. And there are edges running across these. There may also be edges here. Yeah. Just put some edges here and so on. This is the set S, this is the set G minus S or V minus S. Let's just call this S complement. And these edges are the edges in C. So you can look at edges in C to be contained in the set S cross S bar. So it picks one from S and the other from S. So one of its poles. So it's like a bridge. One pole is in S, the other end of the bridge is in S complement. Okay, we know that S intersection is complement. So it's like you have partitioned the set of vertices based on the edges in the cut. Okay. So now if I pick, let's say, X here and Y here. Okay. Let's take an X in the set S and Y in the set S complement. So there is one vertex here, special vertex, and this is also special vertex. So these are two vertices in the original graph. Right? So in the graph G, X and Y belong. So X and Y are actually in B. Okay. So either this edge XY, this is in the graph. Okay. For every pair of XY that you choose, either this is possible for all X and Y, right? For every pair, it will somehow, this cut was so nice. So you picked an arbitrary edge cut, but somehow this cut was so nice that if you looked at the way it partitioned the vertex set, there was always an edge that crossed this cut, sort of, right? One endpoint was in S and the other endpoint fell in Y, and these two were adjacent in the original graph. Or if this does not occur, definitely you know that there are a pair of vertices XY, X is in S, Y is in the complement, such that this edge is not the original graph. So these are the two possible cases, right? Is this clear? So what I want to do out of this right now is I have to use these this case one by one, and I have to construct a vertex cut out of this. But is the story so far clear?
Yes.
Okay. So let's look at the first case. I hope it's clear to everybody. I don't see, not see, so you have to raise questions if you have. So let's look at the first nice case. Okay? So no matter what X, what Y you pick here on either side, this XY is an edge in the original graph. Remember that this X fell on one side and Y fell on the other side because of the cut that you chose. Okay? Okay. So now, if this is true, right, for all X in S and Y in the complement of S, let's say XY is an edge. Then what can you comment about the size of S and S complement? So you have S here, you have S complement here. Let's pick an X here. No matter what Y you pick, I know that this edge is in the graph. These edges are all in the graph. So this vertex X has S complement many neighbors, right? The size of S complement many neighbors. The next vertex, that also has so many neighbors. The next vertex, that also has so many neighbors, and so on. So what can you say about the size of the cut?
Is that C mod C is equal to mod S into mod S bar.
This one. Is that what you're trying to say? I could not hear.
Yes.
clearly, but okay. So the size of the cut. So what it means is that all the edges are crossing the cut. That is what in English, that's what we are saying. Right? So you would define an edge cut, and every edge is crossing the cut. Luckily, it actually partitioned the vertex such that whenever there is an edge, one of them fell this side, one of them fell the other side. You got lucky with this. So how large can this size be? This one. Right? How large can the cardinality of this be? This is at least how much? So let's say the size of S is R. So it's R times N minus R for some R. So how large should this set be? It's at least N minus 1. So we have that the size of the cut, H cut, is at least N minus 1. So what does this mean? So lambda of G is at least N minus 1. Right? So we are looking at the size of the smallest cut. Right? So lambda of G is that. Right? It's the smallest number of vertices you have to, edges you have to remove so that the graph becomes disconnected. So this is at least N minus 1. And I know that kappa of G is at most N minus 1. Right? So I have kappa of G is less than or equal to lambda of G. But this is this nice case when the cut was so nice such that it put one set of vertices on one side and the other set of vertices on the other side, and every edge was crossing from this set S to this set S bar. So in this case, we can argue that we can get a vertex cut out of this. Right? The size of the vertex cut should be constant. So the only thing we are left to do is the other interesting case. So here you know that there are vertices X, so it's not this nice. So there is a vertex X here, and that there is a vertex Y here, such that there is no edge between X and Y in the original graph directly. Okay. So X in S and Y in S bar, such that X, Y is not an edge in the original graph. So what we want to do is I want to construct a set of vertices that disconnect this graph. Okay? So in particular, what I want to do is I want to construct a set of vertices that separate X from Y. So my goal is I have the vertex X here, I have the vertex Y here, or let's put here X and Y here. These two I know are not adjacent, but there might be paths that connect X and Y in G. The only information I have is that there is a set of edges I can remove that disconnect the graph. Now I want to construct a set of vertices that will ensure that if I remove those set of vertices, there is no path from this X to this Y. That's what I want. So I want to disconnect X from Y. In that case, I can say that the graph is disconnected. I have to construct such a set of vertices. Right. So let's look at how this graph would look like. So you have the set S here. You have the set S bar here. And there is this vertex X here. Let's say the vertex Y is here. Now X, I know, is not adjacent to Y. But there can be other adjacent vertices, right? In this set S bar, X can have some neighbors. It's not Y, that's all. Maybe they are like W, Q, P, and so on. And there can be paths like this. So there is a path from X to Y in G. It's just that there is no edge between X and Y in G. Similarly, there can also be paths from X to here, and then these sort of lead you into S. So what are we trying to do? We are trying to disconnect X from Y. So we are trying to understand how many possible ways can there be paths from X to Y. Right? Either you take one step and you reach the set S bar, and then inside that there can be paths to Y. That is possible. Or You take some path, reach within S itself, the set S itself, and take one step to get out of S and reach S bar. And then here there can be a path. These things are possible. Is this clear? Is the picture clear? So, sorry, was there a doubt?
Yes.
Okay, okay. So this is clear, right? So whenever there is a path from X to Y in the graph, this is how it can happen. Either you take one step into S bar and then take a path, or take a path and then take one step, move into S bar and then take another path. So now I want to remove vertices from the graph such that all these paths are all cancelled. So what do I know? I know that a path from X to Y, this should definitely go through the neighbors of X. Right? So you have to go to the neighbors of X and then you have to take a path to Y. So the only two possibilities are either the neighbors of X are in the set S itself or they are in the set S bar. So these are the two possibilities. So these two neighbors of X are in S with another color, and these three neighbors of X are in S bar. So let's give a name to this set. Let's call this B. So B is the set of neighbors of X in the set S bar. And let me call this set A. So how do I write this set in English, right? So what I know is if X is, so this is more English, there's no math. If X is connected to Y via a neighbor in S, right? So if this is what happens, then it has to reach one of the vertices in A and then get out. So we call this, then the path has to reach one of the vertices in A. Right? So either it has to reach the vertices in A or it has to reach the vertices in B. So now can someone give me a vertex cut from these two sets?
Ma'am, we can just remove all the vertices in A and B.
So what
Just
he's saying is A union B, right?
Yeah.
Is a cut set. What? Is this clear to everybody? If there are any questions, we can clarify that. So if you remove all the vertices in A and all the vertices in B, then definitely the graph will be disconnected in the sense that there will not be a path from X to Y. So originally the graph was connected, now you have disconnected the graph. So this is a cut set. The only thing we are left to do is to estimate the size value. Okay. So now this question.
A and B are distant, right? So we can just write mod A plus 1B instead.
Because
And
A is
now-
inside S and B is inside S. Okay, so now what do you do?
And now mod A has to be less than equal to mod S minus 1. And mod B has to be less than equal to mod S bar minus 1. So we get the bound of n minus 2, I think.
Right. But you can actually do slightly better. Let's see. So you have the set of vertices in A and they will all move out, right? In one step, they will take you out of S. I'm just trying to do what he's saying, but in a slightly different manner. So these vertices in one step will take you outside, right? And these vertices in one step you'll get inside. And what is this, how many edges are there here in terms of the cuts, the edge cut
Less
that we
than
started with?
Yeah, less than equal to mod C.
Mod C, right? Exactly. So this is anyway at most lambda of G. Is that clear to everybody? Mod C, which is actually mod C, the original cut that we started with. Right. So all of this, either these things take you outside, these things bring you inside. And there are like so many edges only in the cut that we started with. So this means that you have constructed a vertex cut that has size at most the edge cut. So kappa of G is at most lambda of G. So this inequality is true. So if there are any questions about this proof, then so this means that the vertex connectivity is at most the edge connectivity. So here is an exercise. Find a graph G with G strictly less than lambda of G, strictly less than degree of. Right? So you can find graphs where the vertex connectivity is much lesser compared to the edge connectivity. And all of them can be much lesser than the actual like minimum degree of a graph. Okay. So this theorem is due to Whitney. We'll see another theorem due to Whitney. Okay. So now let us say you have a graph G. So let's
Ma'am, for the example or exercise, not sure. Does a wheel graph on more than, I don't know, 5 vertices work?
try.
I'm not sure. Yes.
Okay, so I'm also trying. So I don't know the answer. Let's try. So what is
Kappa of G is just 1. So. Oh, no, it's not. It's
no,
2.
right? No, yeah. This is 3. I don't know if there's any 2 edges that you can remove. Just graph. You cannot, right?
Yeah, no, this does work. Sorry.
Yeah, please try this. But there are many graphs. Sorry.
Does the equality hold depend on if it is complete or something? For complete, the equality will go.
Yeah, so all of these we will assume that the graph is not complete. If it's complete, then everything is n-1 takes, right? So yeah. So your question is,
if a graph is not
leave, right?
if a graph is not complete, then this will always hold. Is that so?
I don't.
My question.
So. Let me try to think about it. Yeah, if it's a complete graph, it will hold. But if you're saying that if this holds, then it should only be a complete graph. This holds with equality.
If equality holds, then it should be complete.
I don't think so.
Don't think that is.
Because in the original graph that you drew, the like counter example graph, I don't know. One of the first graphs you drew, I think in that only kappa of G is equal to lambda of G.
These ones?
Yeah, I think G3 only works. I'm not sure.
Yeah.
Yeah,
So,
in G3, removing C or just deleting CD is
right. Yeah. So this has vertex connectivity and edge connectivity 1, right? But it's not. Yeah. So it's not okay. So this is great, right? So he asked the right question. So he's asking about when can you say that a graph is this much connected? Right? So what we said is if the connectivity is at least k, then you can say that the graph is k connected. Are there other ways to describe this than just sitting and removing the set of vertices and checking? Right? How will you sit and check? Like you have to try all 1 vertices. Suppose it's not. Then you have to try all pairs of vertices. Then try all triples of vertices and so on. It's like a mundane task. So now we want to say are there other characterizations to determine whether a given graph is like 3 connected, 4 connected, and so on. And the first baby case of this is to understand whether a graph is 2 connected or not. Okay, so when is a graph 1 connected? Like I have to remove 1 vertex and the graph will become disconnected. So it means that the graph has a cut vertex, right? So those graphs are 1 connected. So now we want to look at slightly larger cases. Let's say the graph has at least 3 vertices, and you want to understand whether this graph is 2 connected or not. That is, should I remove at least 2 vertices in order to disconnect the graph? That's what we want to say. So this is Whitney's theorem. So let's say a graph with at least 3 vertices is two connected if something is true. We have to fill that. Okay. So now, what do we mean by connectedness? Whenever I give you two vertices, there must be a path between these two vertices. So now let us say I give you, there is one big, I'm just trying to fill this if only. Okay? I don't want to write it down directly, so I'm going to fill this up. So I have this vertex x, and there's some path, and there is this vertex y, and there is another path. Now, can this edge be a cut edge? Or if I remove any vertex on this path, will the path between x and y be disconnected? No, right?
Edge connected to vertex connected.
Vertex connected. So if I remove any vertex on this path, so let's say there are two paths, P1, there is a path P2. There may be many paths from x and x to y. I'm just saying that there are two paths between x and y in the graph, right? And if you remove any, there are many vertices on this path. Okay, so let's say that this is there, then some vertices are there. If I remove any vertex in the path P1, will x and y be disconnected? That is a question. No, right? Because no matter what vertices on P1 you remove, you will always find a path from x to y via P2. So there was another path that supported you in this process. But what was the property of P1 and P2 that you used? For example, I'll draw another path just to make it interesting. This is another path from x to y. Let's say that there are two paths in the graph, P1 and this P3, right? There's no P2 now, just hide P2. So there is one straight wala path and there's one sinusoidal path. Now, if I remove this vertex, right? Okay, let me use a different color. This vertex. Then will the graph be disconnected? There is no P2. Just forget P2. This vertex also I'm going to remove. Will there be a path from x to y?
No.
No, right? Okay. So what is the property that P1 and P2 had, but P1 and P3 do not have? You had two vertices xy and there were two paths. In both the test cases, there were two paths. In one test case, you had P1 and P2, and it was not useful to remove any vertex from P1 because P2 will help you reach y from x. But when you looked only at P1 and P3, right, removing just this vertex itself helped you disconnect the graph. So what is the property that P1 and P2 had that P1 and P3 does not have?
The paths were through different vertices.
So the answer he's saying is they do not share a vertex. Right? So what property does P1 and P2? The answer is right. So what he said is that they do not share a vertex. So these kinds of paths are called vertex disjoint paths. So we say paths P1 and P2 from x to y are vertex disjoint if they do not share a vertex. So usually these paths are called internally vertex disjoint paths. This is because when you say they don't share a vertex, they actually share x and y, right? So in terminology wise, it's not correct. So in the sense that they don't share any internal vertex, right? Let alone x and y, only those you can share. The ones in between, right, interior to the path, they should not be shared. So internally vertex disjoint paths are two paths or few paths that don't share a vertex. So now we are saying we want to fill this portion. Right? So we are saying you have a graph with at least 3 vertices and you want to say it is two connected. So when I mean two connected, here I mean two vertex connected. That is, I have to remove at least two vertices in order to disconnect the graph. Right? Now, Now can someone try to fill this if and only condition? Let's see.
If there are at least two internally vertex disjoint paths,
Between which two vertices?
ends up to vertices, like all pairs of vertices, right?
So it's two connected if and only if between every pair of vertices, or let's say every pair of vertices in G are connected by at least two internally vertex disjoint paths. So is the statement making sense? It's okay if you were not able to guess this or you cannot see the proof. Is the statement of the theorem clear? So what you're saying is between any two pair of vertices, if you can find two internally vertex disjoint paths, then intuitively it means that you have to remove one vertex from that path and one vertex from this path in order to disconnect the other. And if this is true for every pair of vertices, then you have to at least remove two vertices. Okay? This is the intuitive idea. Now we have to like sit and prove this. So this proof we will do, but I will write down the statement for, okay, maybe we will prove this and then. So let's do one direction. Let's say if every pair of vertices are connected by at least two internally vertex disjoint paths, can there be a single cut vertex?
No.
That's not possible, right?
You can go on from the other path.
Right. So just by definition of internally vertex disjoint, we can say that there is no cut vertex. Right? So then the graph is two connected. You have to at least remove two vertices. Now the hard direction. Okay, the other direction. Suppose G is two connected. This is like the really interesting case. So what you have is, you know that there are at least two vertices that I have to remove to disconnect the graph. Now, given any pair of vertices, let's say UV, right? I must exhibit two vertex disjoint paths from A to B.
So in this case, if since G is like
Connected.
connected, so there must be some paths between. So like if I pick any 2 points U and B, then there must be some paths between U and B. If since G is also two connected, like removing a single like vertex is like it's not going to make it disconnected. Okay, wait. Sorry, I'm so sorry. I'm so sorry. I'm really sorry.
I think you're doing the other direction. Probably.
Yeah.
So this is a hard direction, right? So this is like a constructive thing. You are given two vertices, you have no idea about U and B, and they want you to produce two vertex disjoint paths from U to B. The only information you have is I have to remove at least two vertices, disconnect the graph. That's like the real challenge. You have no idea about this graph that you're trying to work with. So yeah, the proof is not that easy, but it's like doable if I give you the steps. Okay. So the proof is by induction. I only have two vertices UV, right? In my hand. I know nothing about these vertices. So I'm going to do an induction on the length of the path, right, between U and B, or what we will call the distance between U and B. Sometimes we can also call this the shortest distance between U. There are multiple paths. Let's say the distance is just one. So what does that mean? That means that there is an edge from U to B. Now, what is the question we want to ask? So I want to say that there are two vertex disjoint paths. One path is this. So I have to produce another path from U to B. Right? Okay. So does somebody see a proof of this? Just Just out of curiosity, I want to know. Suppose there is only one path, right? There is no other path from U to B.
Like lambda g is greater than like a kappa of g, which is greater than 2. So then, I mean, greater than.
So what he's saying is from this we know that kappa of G is at least 2. Right? This is the information you get out of this thing. Oops, sorry. Just 1 second. Yeah. Okay. So now complete your argument. So we know that lambda of G, this thing, right?
Yes, ma'am. So it's like if we remove the edge UV, there should again be a path from U to V.
Right? So if this was not true, then UV was a bridge in the original graph. But we know that lambda of G is at least 2. So this cannot happen. Is everybody convinced with this? If this other path from U to V did not exist, then it is a contradiction to the 2 connectivity of G. So what this means is, suppose not, okay, so yeah, what he said is right, but I have to write it down. Just this. So suppose the distance is this and there is no other path from U to V, so U to V does not exist, then it means that UV is a bridge in G. By removing this edge UV, I can disconnect the original graph. Then this means that lambda of G is equal to 1. But we know that this inequality is true. So this is a contradiction. So everybody convinced with the base case? Okay. So then we move to inductive hypothesis. So I'm going to assume this is the statement is true for all UV whose distance is less than K. And now we are going to look at the case when the distance is K. So you have two words. Okay, I will just draw this space. So there is this vertex U, there is this vertex V, and there is a path from U of length K. Let's call this path K. So this path has length K. Now, I know that on this path, there must be a vertex, right? Just before D, right? In the sense, it should be something like this. Right? This should be there. Let's call this vertex W. So now I want to use the inductive hypothesis. What should I do? I've already given you one clue. Let's see.
So we can find a vertex disjoint path between U and W. Another
Correct.
like a with respect to the one
Correct.
that
That's the next step. Right, right. So this is the path P. Now I know that the distance between U and W is K minus 1. So by inductive hypothesis, I know that there is a path Q from U to W, that is disjoint from, I just don't know how this path Q looks like. So I will just put this path here. Put the space. I'm going to give another color for this path. This is your path Q.
and there has to also be a separate path between W and V, because otherwise, like if there were no other paths between W and V, then WV would be like a vertex, like it would be like a bridge.
Right?
Yeah.
Right, yeah. That's right. Yeah. But with that path between V and W, let's say, okay, let's just try what he's saying. But from this, you cannot get two vertex disjoint paths between U and V, right? Because they both
Right,
share,
yeah.
share
Yeah.
W. So this statement is true, what you said, but for our purpose, it might not be useful. So you have to remember that at the end, we are going to find a path that is completely disjoint from P. That's the real challenge. Right here. So now, One thing I know is, like what he said, the distance between U and W is k minus 1. So there must be another path, right? And if G is 2 connected, what can I say about G minus W? Suppose I remove this vertex completely. I know that G is 2 connected. Just by removing this vertex, can the graph be disconnected? No, right? So that's not possible. So that's something we have to know. Let's note that. So G minus W is connected as G is 2 connected. That's the time. 10. So now can somebody tell me some observation about U to V in this graph G minus. So let's look at the graph G minus W. Okay, so this vertex is not there. Some other things are all there in the graph. But I know that the graph is connected. Between U and V, what can you say about paths in G minus W?
Since G minus W is connected, so there has to be different paths, like a path from U to V that obviously does not connect W, that contain W.
That does not contain W, right? I
Yeah.
hope that's what you said. Exactly.
Yeah.
That means that there exists another path. Let's call this path P prime from U to V in G minus W. So this path is disjoint from W. That's all you know. You know nothing about how this path will be. So let me use a different color for this. Hope this green will be visible. So now I'm going to draw the path P prime. So let's say this is the case. It's nice case. P prime is like this. So remember that I don't know how P prime will look like. I'm just trying to judge, okay, how P. Suppose this is the case. Now, what are the two disjoint paths? So I'm just going to call this easy. Okay? Remember the P prime can actually be any way. We don't have any handle on how P prime can be. But suppose P prime is this nice green path, then can someone give me two vertex disjoint paths from U to V in G?
Just the green path and the blue path.
Right, the green path and the blue path. So there are like several ways to do this. P prime, and let's call this P. This itself is a are two vertex disjoint paths, right? From U to V in the graph. Or you might as well choose this one, and this one is also fine. So this is the nice case when P prime is like this. So now I will use a different color to get to a harder case. So suppose P prime intersects either P or Q, but not Q. So it's like this. This is possible, or let's say this was possible. So this case is when P prime does not intersect P and Q. So the second case is P prime is independent or is disjoint. Okay, that's what I mean by independent. Of exactly one of P or Q.
Just like the one, it is independent of take that up till W and then W to V, and the other path you can take as is.
So one path you get as is, the
Right.
other path.
P prime and the other path.
Correct.
Which
So P
it is
prime.
in.
So if P prime is, say P prime is independent of Q, then P prime and Q are two vertex disjoint paths. Otherwise, P prime and P are. Right? Agree? These two cases. So now we are going to the real hard case. So the real hard case is when P prime intersects both P and Q. Right? So it's something like this. You start here, you come here, and go. Right? So these are all intersection vertices. The green path is the path P prime.
Can you do this? Consider the first time your path intersects P and the last time the path intersects P, and just stay on P for that period.
Sorry, can you just repeat that? And it was really fast. I meant to follow. Yeah. So what do you want to do?
If like I intersect P twice, this
Uh-huh.
P prime path, I just
Mhm.
go up to P for the first time,
Oh, in this
like
one, right?
using P prime, using P prime,
Okay, like this.
then move along the path and then go at the end. Like the first
This
time
is
and
the
the
other.
last time, if like multiple times I
Right.
intersect.
Exactly. Yeah. So that's all. So once this picture is there, I'm sure all of you would have got it. Right. So what he said, let's just write down. Right. So you must. So this is something you all know. Whatever I drew, you can just retrace. It's exactly retracing a picture. Right. This one and this one. I hope that's what you meant. Okay. These are two parts. So how do you write this in a proof? Right. So that's exactly what we want. I'm sure you've all seen the argument already. Of P not P. So in this case, you know that P prime intersects P. So you are going to look at the last common vertex P prime has with P. Or you can also take it with Q, but I'm going to take this one. Let's call this X. So X is the last common vertex. Exactly what he said. He said the first common vertex. I'm going to talk about the last common vertex. Then you will get two paths. So Q then traverse along P prime. Yeah, and then yeah, okay, let's call this X the way he did it, so that it will just be okay. So you go to U, then use P prime, reach X, use P, then this last common vertex, let's call it Y, it's Y, and then you use the path P prime and reach P. The other path is U, Q, W. Right? So there are two paths, and these two paths are clearly vertex disjoint.
Your method was actually better because mine might have an issue because you might be going into Q later, and it's an unnecessary bother.
No, it will
Your
be the
method
same,
was
but the
just
way you write it, you need to write it as first common vertex and last common vertex. You will probably still get the same, but you have to argue that you won't get back inside Q by mistake. Right?
yes, and that is
So
a
that
little messy, I think, because we can't really guarantee if we take both first common and last common. I
right. So
think.
there is one in between portion that might be missed.
Yes, so it's
Yeah.
just better to just take just the last common vertex and just go along original P and then take P prime and then just take Q, and that works
Right, right.
better.
Yeah, yeah.
Ma'am,
So
we
in,
continue.
Recording stopped.
why did something accidentally? Let me just-
Recording in progress.
Yeah, yeah. So there was a question.
No, ma'am.
Got clear? Okay.
I was just like the screen wasn't visible.
Sure, sure, sure. Yeah, yeah. I think I accidentally clicked on something. Yeah, okay. So is this clear? So you are trying to construct two vertex disjoint paths. There are many ways to construct this, but this is the nicest way to do it. So this is the theorem with me. So what is a natural generalization of this theorem?
K connected, K internal.
K connected, right? So how many internally vertex disjoint paths should be there?
Okay, man.
K of them, right? So that is the celebrated Menger's theorem. It's just that the proof is like a bit too complicated. So it's like this Menger's theorem for K equal to 2 is like the base case. So it's a really, it's a nice argument though, just like this, but we won't do it as part of the course. So this is enough for us. But I will just write down the. So you say that G is K vertex connected if and only if every pair of vertices have at least what if between every pair of vertices K internally vertex disjoint paths. So this is Menger's theorem. Yeah, you can find proofs of this theorem in any standard textbook in graph theory, but we will not do it as part of the course. It's a bit heavy for the course. We want to do more topics in graph theory rather than do Menger's theorem. That is why. Okay. So this is about connectivity. So the next topic I want to cover is something more interesting than connectivity, in my opinion. So we will just introduce the topic, give some applications, and then we'll do the theory in the next lecture because I have like only 5 minutes. So here is an interesting application. Let's see how to formalize this in graph. Talk about schedule, timetable. So some of you, when we scheduled the discrete math exam, complained that I have a different exam that is also running in the same time. So I want one of these exams to be rescheduled in a different slot. Or for example, let's say I teach 2 courses. One is discrete math, the other is, let's say, quantum, and Partha also teaches 2 courses. One of them is discrete math, and he teaches some other course with some other time. So we want to ensure a timetable where all of us can like teach whatever courses we are assigned, and there is no conflict. Okay, so let's see this example. So let's say we have like 5 students. All of them are doing discrete math. Right? So this is their, so this is like core course. And then some of them are doing quantum mechanics, some of them are doing graph theory, some of them are probability, linear algebra, some other things, let's say statistics. Okay. So now I want to ensure some way that there is an exam timetable where all of them can attend all the exams without any conflicts. Right? So can someone try to visualize this as a graph? So what's the underlying graph that you want to talk about, right? So there are like 6 subjects. So let's put a vertex for each. Math, quantum mechanics, graph theory. So I have these 6 subjects for which I want to design slots. And let's say there is this, let's say I give the same slot, some afternoon slot, to both discrete math and quantum mechanics. Then there is this person A, right, who cannot attend both the exams, right? So you can attend only one of the exams. So that should not happen. Is the goal clear? So I'll draw an edge between these 2 courses if there is at least one student who is taking both these courses. Right? So this is what it is. And let's also assume that there are students who are taking these courses together. So this is some graph. So now what should I do in order to ensure that I get a timetable, right, where if there is one student who attends both the courses, then these 2 courses must get different slots. So this kind of problems are captured by what? Graph color. So what we want to do is we want to color the vertices of the graph such that, can somebody fill it for me? What is the goal in timetabling? So I'm going to give colors to these vertices. It's a very nice topic in the sense that you will all be interested.
So
Yes.
we color it so that any 2 adjacent vertices don't get the same color.
Exactly, right? So these 2 things I should not give the same color. If I give the same color, it means I'm going to assign the same slot to them. So these 2 things get different colors. Similarly, quantum mechanics and graph theory should get this different colors because there is a student who's taking both the courses. So this is what is captured by graph color. So you are given a graph G. It's a set of vertices and a set of edges. So a proper coloring G is an assignment of colors to vertices in the graph. That is, to the vertex set B, we are going to associate a set of colors. So you can think about it as a map. So if there are k vertices, let's say 1, 2 to k, you can say that there is also a map, right, from C1 to Ck, k colors. We're going to assign these colors to these vertices such that no 2 adjacent vertices get the same color. So such a coloring is said to be a proper color. So suppose I don't tell you what the graph is, I just tell you that this graph has n vertices. What is a trivial proper coloring of the graph? How many colors will be in, there?
And
N colors, right? So you can always assign distinct colors to all the vertices, and somehow like nice, definitely ensure that any two adjacent vertices are getting different colors. Just because all vertices got distinct colors, but you can actually do much better. Right? Maybe you can like reuse the colors cleverly. So one example is complete graph KN. How many colors does a complete graph require? How many vertices? Can you color a complete graph with n-1 colors?
no.
You cannot, right? Suppose you were able to do this. It's like PGM. Then definitely you will find two vertices that have the same color. And these two vertices definitely will have an edge between them because it's a complete graph. Right? So the minimum number of colors that you need to color a complete graph properly is at least n. So this number is called the chromatic number of a graph. So what is the chromatic number? G. So this is denoted by chi of G. So it's the minimum number of colors in proper coloring of the graph. So what we just argued is that chi of Kn is equal to n. Now can somebody tell me what chi of a bipartite graph is? Okay, so you are saying that with two colors, I can always proper color a bipartite graph. So you have two partitions. One partition you give all the vertices red color, the other partition you give all the vertices blue. So now suppose I give you some graph and you are able to actually two color that graph. So you say a graph. So another way of saying this is a graph is K colorable if there exists an assignment of K colors, right? At most K colors to vertices in G such that the edges get different colors. So I mean, yeah, adjacent vertices get different colors. That's what I should write. So in this language, suppose a graph is two colorable. Then what can you say about the graph?
And it's like at least K partite. Like
No,
we
two
can.
colors, two colors.
Okay, then bipartite.
It is bipartite, right? So what we are trying to say is the first thing that we saw is for any bipartite graph is always two colorable. You give both the partitions different colors. Now, if you are able to two color a graph, then you can put all the vertices with red color on one partition, blue vertices in the other partition, and there will only be edges from between red and blue, right? Across them, and within the same partition, there won't be edges. So this means that this is actually equal to 2, right? In the sense that any two colorable graph is bipartite and any bipartite graph is two colorable. So now in the next lecture, we will look at upper bounds and lower bounds. So like what you would have already observed is that chi of G is anyway at most n, right? If there are n vertices, it's anyway at most n. You can give n different colors. But can we do better? Right? Just like for kappa of G or lambda of G, we said that we can look at the minimum degree and say this. Can we do something about the chromatic number? What kinds of bounds can we get? So we will try to prove some theorems here also about coloring. So that's the next thing we want. And the much larger question that we will hopefully answer in the next lecture at least, or I hope that this will be covered in the next lecture, is that suppose I give you the map of the world, right? And I give you this condition that any two neighboring countries should get different colors. Right? How many colors do you need to color the entire map of the world? Right? All the colors, all the countries should get colors, and any two neighboring countries should get different colors. So you can think about it. There are so many countries, like some 200, 300 countries, and how many colors do you require? So this question we want to answer in the end. That's probably like the larger goal. So I will just stop here. It's already about.
Recording stopped.
Yeah, if there are any questions, you can. Okay, if not, we can meet Tuesday.
Thank you, ma'am.
Yeah, thanks.
Thank you, ma'am.